these elements, and V2 is another array having these elements. We can create a new array V3 by stacking V1 on top of V2. Okay. If you look at what is V3, you can observe that V1 has been stacked on top of V2. This is what we call vertical stacking of arrays. Okay. Similarly, you can have repetition performed in stacking, that is V1, V2, V1, V2 returns, okay, 4 by 4 array or 4 by 4 matrix, where the first row is V1, second row is V2, third row is V1, and fourth row is V2 again. Okay. This is what we call vertical stacking of arrays. We'll proceed further and look at horizontally stacking arrays. Assume that we have one array H1, okay, that looks like this, that is np.ones 2, 4. Its shape is 2, 4, so it's a 2 by 4 array. So let us quickly create that. H1 equals to np.ones, okay, it will be 2 by 4. So this is how H1 looks like, and we will create another array H2 whose dimension is 2 by 2. That is H2 equals np.zeros 2, 2. H2 will now look like this. Now we can place H1 beside H2, or rather H2 I want to place it after H1. That is what we call horizontal stacking. That is, you can observe that H2 has been stacked horizontally after H1. This is done using a method called hstack available, or a function called hstack available on NumPy. That is, if I say H3 equals np.hstack H1, H2, then you will find H3 being a new array created where H2 is stacked after H1 horizontally. This is what we understand by vertical and horizontal stacking of arrays. We'll proceed further. Okay. So far we have seen how to perform operations on one-dimensional and two-dimensional arrays in NumPy. Okay. You can go beyond 2 dimensions. You can in fact work on 3-dimensional arrays or 4 or 5-dimensional arrays and so on. Okay. Let us quickly look at how do we deal with 3-dimensional arrays. 3-dimensional array is basically a 2-dimensional array within an array. Okay. That means, okay, we'll create a 3-dimensional array. Okay. A equals np.arange 1, 25, reshape as 2, 3, 4. Okay. What does this do is it will create a 3-dimensional array, okay, where the first dimension is 2, and within 2 I have another 2-dimensional array of the order 3 by 4. Okay, and this array will be filled with values ranging from 1 to 24, that is 25 excluded. So it will be a 2 by 3 by 4 array. That means it will effectively have 24 elements. So if you look at what A has, A looks like this. That is, it has the outermost dimension having 2 rows, and each row itself is a 2-dimensional array having 3 rows and 4 columns. So in the first dimension I have a 2-dimensional array having the order 3 by 4, and in the second dimension, that is within the outermost dimension, I have another array whose order is 3 by 4, that is 3 rows and 4 columns in each row. Okay. So you can visualize it as a 2D array within an array. Okay. So it looks like this, that is outermost dimension, its indices are 0 and 1. Inner dimension is a 3 by 4 array, so its dimensions are 0, 1, 2, 0, 1, 2, 0, 1, 2 and 0, 1, 2, 3. Okay, right. Now this is I and this is j and this is k. Okay, that is 0, 0, 0 gives me element 1. 1, 0, 1, 1, 0. 1 means I am looking at the second 2D array. 0 means I am looking at the first row and 1 means I am looking at 14. Okay, so if you say a of 1, 0, okay, that is, how do we index it? Okay, 0, 0, 1 gives me this element. Okay, 1, 0, 1 gives me 14. That is, 1 means the second two-dimensional array, 0 means the first row in that two-dimensional array, and 1 means the second element. Okay, so that returns me 1. Okay, now in Python I can also perform negative indexing. So the last 2D array is at -1 subscript and the first is at -2. Similarly, 0 is at -3, 1 is -2 and 2 is second row is accessible at -1. Similarly, these are available at -1, -4, -3, -2 and -1. So 0, 0, 1 is same as -2. 0 means -2, that is this, and then -3 means first row and -3 means -1, -2, -3. So I am referring to 2. Okay. Similarly, to access 16, okay, where is 16? 16 is here. So where is it? A of 1, 0, 3. So A1, 0, 3, or you can use negative indexing also. It is -1. This array is -1. So A of -1, -3 and -1. Okay, A of -3, -1, -1, -3, -1 returns me 16. Okay. Okay, what does A of 0 return? Okay, it will return this complete thing. Okay, that is, it will return the first two-dimensional array contained in the three-dimensional array. That is, look at this. This will return me the first two-dimensional array. Okay, A of 1 returns me the second two-dimensional array. Okay, what does A of 0, 1 return? Okay, obviously A is this, A of 0 is this, and A of 0, 1 is this. Okay, so it should return 1, 2, 3, 4. So A of 0, 1 should return me the second row, that is first two-dimensional array, second row. Similarly, A of 1, 0 should return me the first row of the second two-dimensional array. This is how we can work on or index elements in a three-dimensional array. Okay, so it is easier for us to understand how do we index a three-dimensional array if you work around or work on the indexing of a three-dimensional array. Outermost index is 0, 1 in this case, inner index is 0, 1, 2, and innermost index is 0, 1, 2, 3, because our array was of, if you look at the shape, it is 2, 3, 4. So the first outermost index ranges from 0 to 1, inner index ranges from 0 to 2, and innermost index ranges from 0 to 3. Okay, so if you understand that, then it becomes easier for us to access the elements using index on a three-dimensional array. Okay, how do we slice? Okay, in the previous session we saw how do we slice a one-dimensional array and two-dimensional array. How do we slice a three-dimensional array? For slicing a one-dimensional array, we used start, stop, step. And for slicing two-dimensional array, we used start, stop, step, comma, start, stop, step. This is for the first dimension, and this is for the second dimension. And since we are dealing with three-dimensional array, we'll have start, stop, step for the outermost dimension, start, stop, step for the inner dimension, and start, stop, step for the innermost dimension. That is I, which is the outermost dimension, j is the inner dimension, and k is the innermost dimension. So we need to use, in order to get a slice of a three-dimensional array, we have to use start, stop, step 3 times. One for the outermost, one for the inner, and one for the innermost. Okay, let us look at a few examples that will demonstrate how do we slice a three-dimensional array. Okay, now look at this array. Okay, this we have already created. Okay, now I want to slice 1, 5, 9 and 13, 17, 21. Okay, out of this three-dimensional array. So how do I do that? Okay, look, I am spanning the entire three-dimensional array. So I want to deal with both the two-dimensional arrays contained in the outermost dimension. So the first will be colon, that is for all the two-dimensional arrays. Second will also be colon because I am dealing with all the rows of both the dimensions. And innermost will be 0, colon 1, that is I want to get the first column. So 0, colon 1 means 1 excluded, so it will return me the first column alone. Okay, so let us look at this. A is this, and I want to retrieve 1, 5, 9, 13, 17, 21. So I can say colon, that is all the two-dimensional arrays, colon, that is all the rows of both the dimensions, that is inner dimensions, and 0, comma 1, that is I want to retrieve only the first column. So this will return me 1, 5, 9 and 13, 17, 21. So I have got the slice that I wanted. Okay. Similarly, look at this. Okay, I want to slice 5, 7, 9, 11, 17, 19, 21, 23. Okay, so how do we slice this? To slice this, again the first will be colon, that means I want to work on both the two-dimensional arrays. Second will be 1 colon. Why 1 colon? That is I want to work on second and the third row of both the two-dimensional arrays. So second is at index 1, so colon means all the remaining rows, and 0, colon, colon 0 till the end in steps of 2, that is retrieve this step by 2, retrieve this step by 2, retrieve this, and so on. Okay, so if I show this, A of colon, that is all both the two-dimensional arrays, and I want to work on second and third rows, and I want to retrieve first column of each row and the subsequent columns in steps of 2. So this will return me 5, 7, 9, 11, 17, 19, 21, 23. That is 17, 19, 21, 23. This is what the slice that I wanted to get. So that is done using this command. Okay. So far we have seen indexing and slicing one-dimensional arrays and three-dimensional arrays. This is what we call basic indexing. Okay, that is indexing and slicing together are called basic indexing in NumPy. Using basic indexing, we can access a particular element using an integer index, which can be a single for a one-dimensional array, or row column for two-dimensional array, or 3 indices for a three-dimensional array, and so on, or a group of elements in an array using start, stop, step for 1D, okay, repeating it twice for two-dimensional array, or repeating start, stop, step for 3 times for a three-dimensional array to retrieve a slice of a 1D or a 2D or a 3D array. However, in advanced indexing, we can use an ND array itself as an index. Interesting, right? Okay. The ND array should be of either integer type, okay, in that case we call that as advanced integer indexing, or the ND array can be of Boolean type, in which case we call that as Boolean indexing. So advanced indexing comes in two flavors. One is integer indexing and the second one is Boolean indexing. Okay. However, the point to note here is we can use an ND array itself as an index. Okay. How do we do that becomes clear with a few examples that I will demonstrate now. Okay. So I'll first look at integer indexing. Okay. Now, a equal to np.a range 1 to 10 will return me an array that starts from 1 up to 9 because 10 excluded. And observe that I want to retrieve these values which are highlighted in red color, that is 2, 5 and 6. Okay. So how do I do that? Okay. I need to create an index array. Okay. An index array. Okay. What are the indexes of the element that I want to retrieve? 2 is available at index 1 and 5 is available at index 4 and 6 is available at index 5. Okay. So first we need to, in order to access the highlighted elements, we'll first create an index array. Okay. So index array is, I want to retrieve 2 which is at index 1, 5 which is at index 4 and 6 which is at index 6. Once we do that, then we can directly use this index array as an index for NumPy array. Okay. That is, use the index array as index, that is a of index will return me element at index 1 which is 2, element at index 4 which is 5 and element at index 5 which is 6. Okay. Simple, right? If you don't want to create index arrays, then you can also use lists, essentially because in advanced indexing you can use list as an index because list is also a sequence. Just as an array is a sequence, list is a sequence. Okay. Let us demonstrate this. Okay. Take a as np dot a range 1 to 10. Okay. I want to, a is this, I want to retrieve, let us say 3, 6 and 9. Okay. How do we do that? Index array equals np dot array, 3 is at index 2, 6 is at index 5 and 9 is at index 8. And then a of index will return me 3, 6 and 9. As I said, you need not have to create an index array. You can directly use a Python list as what? A of Python list will be 3, 6 and 9. Okay. This, okay, that is, no, sorry, it cannot be 9. Okay, that is 3 is at 2, 5 and 8. Okay. So this will also return me the same thing, that is 3, 6 and 9. Observe that this is a Python list, whereas this is a NumPy array. Okay. So integer indexing is simply create an array of index, use the index array as an index over the NumPy array to retrieve the specific elements that you want to retrieve from the NumPy array. Okay. Let us look at a few more examples. Okay. B is a NumPy array that looks like this. That is, I have used reshape method. Okay. So this will give me a list or an array from 1 to 9, and I am reshaping it to be a two-dimensional array of the order 3 by 3. So this will be the resulting NumPy array B. Okay. I want to retrieve, or I want to index 3 and 7. Okay. How do I do that? Okay. Earlier what we saw was advanced indexing on a single dimensional array. On a two-dimensional array, okay, note where is 3 and where is 7, and then you can index it. As how? Okay. 3 is on row 0 and 7 is at row 2. Understood? Okay. Row index of element 3 is 0 and row index of element 7 is 2. And what is the column index of element 3? It is 2, and column index of element 7 is 0. Okay, so this will retrieve me 3 and 7. Okay, we'll quickly show that. A range 1 to 10, reshape 3 by 3. Okay, B of 0 2. Okay, B is this, and B of 0 comma 2 comma 2 comma 0 will give me 3 and 7. Clear? Okay. Now, what if I want to retrieve only these elements, 4, 6 and 8? Okay, where is 4? 4 is at 4 is at row index 1, 6 is at row index 1 again, and 7 is at, or rather 8 is at row index 2. Okay, and within those rows, where are the column positions? Column index 0, column index 2 and column index 1. So your indexing looks like 1 1 2 comma 0 2 1. This will return me 4, 6 and 8. Okay, so this is what we saw earlier, that is 0 2 1. Using advanced indexing, we can access elements repeatedly also. Okay, look at this example. A is 1 to 9, an array containing elements 1 to 9. If I say 1 4 1 4 1 4, okay, what is the element at index 1? It will be 2, and what will be the element at index 4? It will be 5. Okay, essentially because if I say np dot a range, okay, 1 to 10, A is this, so 1 is 2 and 1 is 2 and 4 is 5. So it will continuously, repeatedly access 2 5 2 5 2 5. So we can also access elements repeatedly using advanced integer indexing. Okay, let us look at Boolean indexing. That is, instead of an integer, we can use Boolean expressions as an index. Okay, so look at the power, okay, of accessing the elements of an array in NumPy. Okay, the elements, okay, that satisfy the Boolean expression are returned. Okay, for example, assume that we have IA marks scored by 5 students in 3 tests stored in an array. Okay, in order to simulate that, okay, I said there are 5 students and 3 tests. Okay, so I need to create, or I need to generate 30 values. Okay, 5 students and 3 tests. Okay, so 1 to 31, that is 1 to 30, within that range, that is the marks are between 1 and 30, maximum marks being 30. So I want to generate random numbers within the range 1 to 31, and I want to create an NP array of the order 5 by 3. Okay, so let us create that. A equal to np dot random dot randint 1 comma 31. Okay, and then size is 5 students and 3 tests. So A looks like this. Okay, first student has scored these many marks, second student has scored these many marks, and so on. Okay, assume that your professor wants to add 3 grace marks to all the students or all the marks that are less than 15. Then we can simply do that by saying A of A less than 15 plus equal to 3. That is, A of A less than 15 is the Boolean expression. So wherever you find an element where this Boolean expression is satisfied, increase that value by 3. This is what the statement looks like. So it first encounters this element, that is 2. 2 is less than 15, so 3 is added there. 4 is less than 15, 2 is added. 12 is less than 15, 3 is added, and so on. So look at the resulting list, resulting array. You can observe that 2 has been changed to 5, 4 has been changed to 7, 12 has been changed to 15, 11 has been changed to 14, and so on. Okay. Think of a scenario how you can do it in Python lists, or for that matter C or C++ arrays. You need to set up a loop, check for condition, and then if the condition satisfies, do this operation. But you can simply perform Boolean indexing. Wherever this Boolean expression is true, perform this. Okay, simple as that. Okay. We'll look at another example of Boolean indexing. Assume that we have recorded temperature of 10 cities in a NumPy array. Okay, in order to simulate that, we have assumed that the temperatures range from 10 degrees to 39 degrees. So I have generated random numbers in the range 10 to 39, whose size is 10. Okay, since it's a one-dimensional array, I need to specify a tuple. Okay, so A equals np dot random dot randint. I want to generate values between 10 to 39, and I want to specify the size to be 10. So this will generate an array or a vector containing 10 values, each value in the range 10 to 39. So A will look like this. Okay. I want to find temperatures which are more than 25 degrees. So what do? I will use this array, and wherever there is a value that is more than 25, return that. Okay, return that. So what does it return? It returns 36, 38, 39, 31, 33, but doesn't return the remaining values 21, 20, 12, 14, 22, because the condition is not satisfied. Okay. If I just say A greater than 25, then it returns the entire array and indicates wherever the condition is true. That is, wherever the temperature is more than 25, it is indicated as true, and the remaining cases, the condition or the value is indicated as false. So you can use this array to process the NumPy array, original NumPy array further. Okay. So this adds a lot of value for mathematical application where you are dealing with data. Okay. So Boolean indexing and advanced indexing are of great help because they result in faster operations, and you don't have to set up a loop to do all this. Okay. Now we'll go to the next topic, that is array manipulation. We'll here look at two functions, that is transpose and swap access. We'll first look at the function transpose. Transpose is available both as a function as well as a method. Okay, you'll understand that shortly. The syntax is numpy.transpose array comma access equal to none. Okay, for the time being, don't look at access equal to none. Transpose rearranges the dimension of a given NumPy array in the reverse order. So if it's a 2 by 3 array, transpose will give me a 3 by 2 array. Okay. Observe that it doesn't copy the resulting array. That is, the original array is not affected. It is retained as it is, but transpose returns me a view of the resulting array. You can always assign it to a new ND-array object to create a new array, new transposed array. For example, A1 is this, that is, A1 equals np dot, okay. Remember that I have already imported NumPy as an alias np, so I am using np rather than NumPy. Np dot, okay, I will create okay. My Anaconda spider has crashed. I'll start that. Okay. Now, at this point, what happens is np dot transpose A1 will return me an array of the shape 2 by 5 because the original shape is 5 by 2. Okay. We can also write it as A1 dot transpose. That is what I said. The transpose is available as a function. So you can say np dot transpose A1, or transpose is available as a method. So on the now nd array object A1, you can use transpose as A1 dot transpose, or there is a shorthand for transpose as capital T. So each of these three do the same thing. Okay. If my okay, well, I will be demonstrating that once the spider is up. Yeah, it is about to start. Okay, fine. Similarly, we can transpose three-dimensional arrays also. Okay, first we'll complete this. Okay. Now I of course have to now import NumPy all over again because spider had crashed. So I will create an array 1 to 11 and I will reshape it as a 5 by 2 matrix. A looks like this. If I say np dot transpose A, it gives me transpose array. So the shape of original array was 5, 2, and the shape of transposed array, okay, that is you can always find out transpose A and look at its shape. Its shape is 2 by 5, whereas shape of A is 5 by 2. So basically transpose will reverse the dimensions. Given an array of m by n, it gives you a view of another array whose order will be n by m. Okay. Now we can also transpose three-dimensional arrays. Okay. For example, let us assume that I have a three-dimensional array created out of values 1 to 24, whose shape is 2, 3, 4. This is how it looks like. Okay. It's a two-dimensional array having two more two-dimensional arrays, that is outermost index is 2 and it has 2D arrays of the order 3 by 4. So the original shape of array A is 2, 3, 4. When you transpose it, you get a three-dimensional array whose order is 4, 3, 2. That is, this is exactly reversed. 2, 3, 4 becomes 4, 3, 2. Okay. So transpose has no effect on one-dimensional arrays because one-dimensional array has single dimension. There is no point in reversing a single dimension. Okay. That is, if you take an example, A equal to np dot array 1, 2, 3, 4. Okay. A is a vector, a one-dimensional array. Okay. So A dot transpose doesn't have any meaning. It remains the same. Okay. However, if A were this 1, 2, 3, 4, okay, A dot transpose gives me 1, 2, 3, 4. Observe the difference between this and this. Okay. Here it's a list that you have specified. Okay. So it becomes a 1 by 4 array, whereas this is simply a vector, whereas this is a 1 by 4 arrays where it has 1 row and 4 columns. And when you transpose that, you get a resulting array having 4 rows and 1 column. So its shape is one, 4, whereas A dot transpose shape will be okay, that is resulting array. Okay, let us look at np dot transpose a dot shape. This will be 2. Okay, no, we haven't created it, but essentially it becomes a 4 by 1 array. Okay, well, we said there is an access parameter for transpose function. Okay, if we omit access parameter for the transpose function, it performs the reverse, okay, creating a transpose array which has the reverse dimension. So if it is a 4 by 3 matrix, it becomes a 3 by 4 matrix using transpose if you don't specify the access parameter. Okay, that is, access parameter can be either 0, 1 or 1, 0 for 2-dimensional arrays. Okay, so if you specify 1, 0, it performs reverse, that is 1 and 0 are reversed. Whereas if you specify the access parameter as 0, 1, then it returns you the same array. That is, if A1 is this, that is it's a 5 by 2 matrix, then transpose one access parameter as 1, 0, then it gives you transpose. Whereas if you specify access as 0, 1, it gives you the original matrix itself. So if you don't specify access parameter, it is as good as saying access equal to 1, 0. This is by default if you don't specify the access parameter for the transpose function. Whereas if you do specify the access parameter, then if you specify 1, 0, it performs the reverse, that is, it actually gives you the transpose. If you specify 0, 1, it gives you the same array back. Okay. Well, let us look at the access parameter for a 3-dimensional array. So np.arange 1 to 24, reshape it as 2 by 3 by 4 array, and now we want to transpose it to get a 3 by 4 by 2 array. Okay, if you transpose it as it is, it will give you a 4 by 3 by 2 array. That is, if I say a equal to np.arange 1, 25, reshape it as 2, 3, 4, a is this. A dot transpose, or rather np dot transpose a will give me a 4 by 3 by 2 matrix. Okay. However, if you want to get a 3 by 4 by 2 matrix, then how should I do that? Okay. A is this. It's a 2 by 1, 2, 2 by 3 by 1, 2, 3 by 4, that is 4 columns in the inner dimension. So if I perform transpose on it, it will give me 4 by 3 by 2. What if I want to transpose it as a 3 by 4 by 2? Okay, then I have to use the access parameter. So as np dot transpose a with the access as, okay, I want to create it as a 3 by 4 by 2. So original array was 2 by 3 by 4. Okay, if I transpose it, it gives me 4 by 3 by 2. I want to get a 3 by 4 by 2. So where is 3 in the original array? It's at index 0. And where is 4 in the original array? It is at index 2. And where is 2 in the original array? It is at index 1. So in order to get a 3 by 4 by 2 matrix or array, I have to specify it as 2, or rather 1, 2, 0. Okay. Why 1? Because it was 2 by 3 by 4. 2 is at index 0, 3 is at index 1, and 4 is at index 2. Now this will give me a array which has at the outermost dimension 3 rows, inner dimension has 4 rows and 2 columns. So it effectively is a 3 by 4 by 2 array. Okay, if you look at the shape of this, you'll understand that it's a 3 by 4 by 2. Whereas if you just say np dot transpose A, and if you look at the shape, it will be a 4 by 3 by 2. Okay. I hope you understood this concept. Okay. So this is what we just discussed. You can look at the slide and understand for yourself. If we don't specify the access parameter, transpose function by default will rearrange the dimensions in reverse order. However, if you want to be specific as to I want the dimensions to be reordered as this, then you can always use access parameter to specify the shape as 3 by 4 by 2 or 4 by 3 by 2 or 4 by 2 by 1 and 2 by 4 and so on. Okay. And the second function that we are interested to look at is swap access. That is, how do we swap access? The general form is numpy.swapAccess, the ND array, access 1 and access 2, which we want to interchange. So swap access is used to interchange the access of an array. Here basically access 1 is swapped with access 2. For example, A is a ND array whose dimension is 1 by 3. Look, observe that it's an list that I have provided. So it becomes 1 row and 3 columns. And swap access 0, 1, that is swap the access 0 with 1, it will give me a 3 by 1 array. Okay, that is, if A is an NP array having 1, 2, 3, 4, okay, A's shape is 1, 4. Okay, if I say np dot swap access A, swap 0 with 1, it gives me a 4 by 1 array. Okay, this is equivalent to swap access A 1, 0. Okay, it remains the same, right? Okay, swap 0 with 1 or swap 1 with 0, it results in the same array. Okay, that is for, okay, and we'll look at another example of swapping accesses. We'll create an ND array, okay, whose dimension is 2 by 2. That is, it will have 2 rows and 2 columns. Okay, swap access 0, 1. Okay, here first row becomes the first column and the second row becomes the second column. That is, first row 1, 2 becomes first row in the resulting resulting array, and 3, 4, which is the second row, becomes the second column of the resulting array. Okay, we'll show it. A equals np dot array 1, 2, 3, 4. Okay, A is a 2 by 2 matrix. np dot swap access A and swap 0 with 1. Okay, it will give me 1, 3, 2, 4. That is, first row becomes first column, second row becomes second column. Okay. Okay. Again, as we said, okay, np dot swap access, okay, 0, 1 is same as np dot swap access A, 1, 0. Okay, this will result in the same thing, because 0 is swapped with 1 or 1 is swapped with 0, it remains the same. It means the same. Okay, we'll look at how do we use swap access for 3-dimensional arrays. Okay, well, this creates a 3-dimensional array of the order 2 by 3 by 4 with 24 elements. Okay, this we already have seen. And if you want to swap row and column of each 2-dimensional array, then we can say np.swapAccess A, 1, 2. That is, I don't want to touch on the outermost index, outermost dimension, that is 0. I want to swap inner dimensions, that is the 3 by 4 matrix, which is the inner dimension. I want to swap inner dimensions row 1 with 2, that is swap row and column of the inner two-dimensional array. Then I can say swap axis a comma 1 comma 2. In this case, the first row becomes the first column, second row becomes the second column, third row becomes the third column of the first 2D array. Similarly, first row becomes the first column, second row becomes the second column, and third row becomes the third column of the second two-dimensional array. So the shape of the original array was 2 by 3 by 4, whereas the shape of the resulting array will obviously be 2 by 4 by 3. Okay, understood? Because here I have 3 rows. When I swap, I will get 4 rows. And I have 4 columns. When I perform swap, I'll have 3 columns. So this will be a 4 by 3 array, and the outermost dimension remaining the same. So you still have 2 arrays, two-dimensional arrays. Okay, we'll demonstrate that. A equal to np dot a range 1 comma 25. Reshape it as 2 by 3 by 4 array. So A looks like this. If I say np dot swap axis A, I want to swap first and the second axis. Okay, then it gives me 1 3 9 2 4 6, that is 1 2 3 4, which is the first row, becomes the first column in this case, second row becomes the second column, third row becomes the third column. So the shape of A is 2 by 3 4 by 4, whereas the shape of the resulting array will be 2 by 4 by 3. Okay, apart from these array operations that I can perform easily using NumPy, NumPy also provides me a rich collection of mathematical operations, that is mathematical functions. So it provides standard trigonometric functions, functions for arithmetic operations, and functions for handling complex numbers, and so on. Okay. For example, let us look at 2 arrays, A having 4 elements, it's a vector, and B is another vector having 4 elements. I can perform all basic mathematical operations as well as compound assignment or assignment operations on both these arrays. That is, I can say A plus B, it returns me element-wise addition, A plus 2. Okay, you can add a constant to each. Okay, like A equals to np dot array 1 2 3 4, B equals np dot array 1 1 1 1, okay. A plus B gives me a view. It doesn't affect either A or B. It gives me a view of the resulting array, which looks like 2 plus 2 3 4 5. Individual elements of A are getting added with the corresponding elements of B. If I just say A plus 5, 5 is added to each element of the array, and you get a view of the resulting array. A remains as it is. Similarly, A plus equal to 2, okay, here A gets affected. A becomes 3 4 5 6, because this is as good as saying A equal to A plus 2. Okay, so individual element of A is getting added with 2, and the resulting array is getting assigned to A. So A becomes, okay, now it will be 5 6 7 8, because 2 is added to 3, 2 is added to 4, 2 is added to 5, and so on. So all these basic operations are permissible on NumPy arrays. Okay, and it performs it on the entire array. Okay, you don't have to set up a loop to achieve this. Okay, and this is possible for 2-dimensional arrays also, or for that matter 3-dimensional or subsequent dimensions also. Okay, similarly sine, cos, okay, exponentiation, okay, all of these operations are possible on entire NumPy array. That is, you can perform or you can compute sign of each element. Okay, for example, np dot sign of a gives me these values. That is, sign of 5 is this, sign of 6, which is the second element, is this, sign of third element is this, and sign of fourth element is this. Look at the power of NumPy arrays. That is, you simply perform this operation on each element of the array. Okay. Similarly, you can get exponentiation, exponent or log, okay, which is the inverse of exponent, using functions such as exp and log. Similarly, okay, if I have an NP array that looks like this, then I can round the values using a round, okay, which will perform rounding of the array elements. Okay, let us look at this quickly. A equals np dot array 0.5, 1.5, 2.5, 3.5, 4.5. A is this. A dot or np dot a round a gives me 0, okay, 2.0, 2.0, okay. Interesting, right? 0 is rounded to 0, 0.5 is rounded to 0, 1.5 and 2.5 both are rounded to 2. That is, it evenly rounds. That is, it rounds it to the nearest even number. So 1.5 is the nearest even number is 2, and 2.5's nearest even number is 2. 3.5's nearest even number is 4. Similarly, the nearest even number of 4.5 is 4.0. Okay. You also have functions such as ceil, floor, ceil, which will take it to the next value. Okay, instead of a round, if I say ceil of a, it gives me 1.0, 2.0, 3.0, because the nearest higher integer is 0.5, nearest highest integer for 1.5, nearest value higher value for 1.5 is 2.0, and so on. Similarly, np dot floor is literally bringing it down. Okay, ceil is bring it up and floor is bring it down. So np dot floor of a gives me 0, 1, 2, 3, 4, because the nearest lower value of 0.5 is 0, nearest upper value of 0.5 is 1. So floor brings it down to the nearest value, whereas ceil will bring it up to the nearest next value. Okay. Similarly, you have trunk which will truncate the values. So there's a typo here. trunc, trunk of a gives me 0, 1, 2, 3, 4. That is, this is the original array. So 0.5 is truncated, you get 0. 0.5 is truncated, you get 1, and so on. Okay. Reciprocal, which will give me the reciprocal of array elements, like np dot. Okay, let us create an array a equal to np dot array 1, 2, 3, 4. np dot reciprocal of a gives me 1, 0, 0, 0. That is, 1 by 1 is 1, 1 by 2 is 0, 1 by 3 is 0, because the elements are integers, so it performs integer division. Whereas if I specify d type as float, then np gives me 1.0, because 1 by 1 is 1.0, 1 by 2 is 0.5, 1 by 3, which is a reciprocal of 3, is 0.33, 1 by 4, reciprocal of 4 is 1 by 4, which is 0.25, and so on. So in one go, you can get reciprocal of all the elements contained in the NumPy array using functions such as reciprocal. So in this way, okay, divide, which is same as division operator. So in this way, NumPy provides me a rich collection of mathematical operations in the form of either functions or methods. Each of these that we saw, okay, can be used as methods on a ND array object or as a function using as np dot name of the function. Okay. With this, we close our discussion of NumPy arrays, and from the next session, we'll be looking at the last unit of your course, where we'll be looking at SciPy, that is scientific Python, and there we'll be looking at how powerful SciPy can be in order to work on scientific and mathematical problems such as optimization problems or integration problems and so on. Okay, this will be taking up in the next session. We'll stop for the day.